Assalamualaikum dan salam sejahtera. Thank you for viewing our video. In the next few minutes, we will present and discuss our video topic about passive filter RCL band stop filter. But firstly, I would like to introduce my team members. My name is Ana Norizai Ain binti Ahmad and my fellow members Muhammad Faiz bin Sofian with Muhammad Ridwan Aminuddin bin Zadi Ismail. So, sit back, relax and prepare to embark on a captivating journey of discovery with our group as we present our video. Abstract. A band stop filter, also known as a notch filter or band reject filter, is an electronic filter that allows all frequencies to pass through except for the specific range of frequency, which are attenuated or blocked. It is the opposite of a band pass filter, which allow only a specific range of frequencies to pass through. The purpose of band stop filter is to eliminate or reduce the amplitude of signal within a particular frequency range while allowing another frequency to pass through unaffected. Can be useful in various applications such as audio processing, telecommunication, signal analysis, and interface rejection. So, for the introduction, what is the band stop filter? Band stop filter is a filter that prevents a band of frequency between two designated values, omega 1 and omega 2, from passing a variable known as a band stop, band reject, or notch filter. There are different types of band stop filter, including active filter and passive filter. Active band stop filter use active components like operational amplifiers, while passive band stop filter use passive components like resistor, capacitor, and inductor. The design of a band stop filter depends on the desired characteristic, such as the center frequency of the stop band, the bandwidth of the stop band, and the level attenuation. Common designs include the twin T-notch filter, the multiple feedback filter, and the Sallen-Key filter. Application. The application of the band stop filter including the following. In electric guitar amplifier, image and signal processing for reduction of noise, reduction of statistics on a radio. In biomedical instrument for the removal of noise. In DCL internet service and noise reducer. The band stop filter are used for removing interface on the line. In audio application like PA system, example public address system in the filter is used. In optical communication technology for eliminating the distort, the band stop filters are used. One of the examples of this Raman spectroscopy. Now I will tell the procedure of circuit. Determine design specification, center frequency FC, specify the desired center frequency of the band stop filter. Bandwidth. Determine the acceptable range of frequency to be attenuated. Attenuated level. Specify the desired level of attenuation in the stop band. Calculate the value of resistor R1, resistor R2, inductor L, and the capacitor C using the given values and the following formula. R1 6 ohm, R2 4 ohm, L 1 millihenry, C 4 microfarad. By designing the circuit, we can calculate the component value and then reconstruct the RCL circuit by using multisim software.
For the calculation of RCL band stop filter, we have to determine the impedance of combination at output. There are three combinations, which is Z equal R parallel to S. For the calculation of RCL band stop filter, we have to determine the impedance combination at output, which is Z equal R parallel SL plus 1 over SC, Z equal R SL plus 1 over SC divided by R plus SL plus 1 over SC, and then Z equal R times 1 plus S squared LC divided by 1 plus SRC plus S squared LC. After that, we determine the transfer function, which is H equal to V naught S divided by V1 S equal to Z times S divided by Z times S plus R naught, to the H equal R times 1 plus S squared LC divided by R naught plus SR R naught C plus S squared LC R naught plus R plus S squared LCR. And then we substitute the S to J omega in equation, which is H J omega equal to R times 1 plus J omega squared LC divided by R naught plus J omega R naught C times plus. Then we determine the transfer function, which is H equal to V naught times S divided by V1 times S equal to Z times S divided by Z times I. After that, we determine the transfer function, which is H equal V naught times S divided by V1 times S equal Z times S divided by Z times S plus R naught, which is H equal R times 1 plus S squared LC divided by R naught plus SR R naught C plus S squared LCR naught plus R plus S squared LCR. And then we substitute S equal J omega in equation 1. And finally, ZIN equal R naught plus SR naught RC plus S squared R naught LC plus R S squared LC divided by 1 plus SRC plus S squared LC for the equation 1. So that's we put first in equation 1, and then after that we substitute S equal J omega in equation 2. So in equation 2 we have to do Z equal R naught plus J omega R naught C minus omega squared LCR naught plus R minus omega squared LCR divided by 1 minus omega squared LC plus J omega RC. Then, to determine the center frequency, the imaginary part of the impedance is 0, which is I make Z in equal to 0. And then we do the calculation until the last part is omega squared equal 1 over LC, which is omega equal 1 over square root LC. After that, we have to determine the maximum value of H J omega, which is H J omega equal R times 1 minus omega squared LC divided by R naught plus J omega R naught C minus omega squared LCR naught plus R minus omega squared LCR. And we have to determine the H max, which is H equal infinity equal to R divided by R plus R naught, where omega 1 and omega 2, H omega equal to 1 over square root of 2 H maximum. At 1 over square root of 2 times R divided by R plus R naught equals to R times 1 minus omega naught squared LC divided by R naught plus J omega R naught C minus J omega squared LC R naught plus R minus J omega squared LCR. So from the circuit above, we know the value for the R, L and C, and then we substitute for R, L and C. We just put the value and into the formula for the calculation, and at the end we get omega squared equals 2.9 times 10 power of 8 and 2.15 times 10 power of 8. So therefore, omega 1 is equal to 14.663 card per second and 17.029 card per second. So after we calculate the bandwidth, which is B equals omega 2 minus to omega 1, which is 17.029 times 10 to the power of 3 minus 14.663 times 10 power of 3, we get 2.4 card per second. Therefore, the value of the bandwidth of the band stop filter is 2.4 card per second.
Thank you, Mama Faiz, on your wonderful explanations on the calculation of RCL bandstop filter. Assalamualaikum and selamat sejahtera to all the viewers. I will continue the presentation, which is already on its last leg, with the simulation performed on the assignment. Using multisim, which is one of the few circuit design programs to employ the original Berkeley SPICE-based program or software simulations, you can download or use the multisim online for free to get started with this assignment. Moving forwards, you can launch multisim by double-clicking the multisim software on your computer if you already downloaded it, or you can use it online. Click on the file and select New to create a new circuit. From the component library, you can locate and place the following components onto the workspace. For our assignment, we will use three types of component, which is resistor R, choose suitable resistor values based on your design requirement. Capacitors C, select appropriate capacitor value based on your design requirements. And inductors L, choose an inductor value based on your design requirements. Using the wiring tool to connect all the components according to the bandstop filter circuit's configurations. The general configuration consists of placing the resistor and capacitor in series and connecting the inductor in parallel to form an RCL circuit. Double-click on each component to open their properties dialog box. Enter the desired resistance, capacitance, and inductance value for each component. Ensure that the values you enter are appropriate for the frequency range you intend to attenuate. Set input and output by adding a voltage source to represent the input signal and connect it to the appropriate location in the circuit. Similarly, add a load resistor or other output elements to represent the output of the filter. To simulate the circuit, click on the Run button or go to Simulate and select Run to start the simulation. The multisim software will start to analyze the circuit and provide the output waveform and frequency response. Examine the output waveform and frequency response to observe the behavior of the bandstop filter, which will identify the frequency range where the filter attenuates the signal at the most. Calculating bandwidth and center frequency. Well, based on the frequency response, determine the lower cutoff frequency, FL, and upper cutoff frequency, FH, where the filter starts and stops attenuating the signal. Calculate the bandwidth B using the formula B equal to FH minus FL. Similarly, calculate the center frequency Fc using the formula Fc equals to Fh plus Fl divided by 2. To modify and iterate, which is an optional condition, if the obtained bandwidth or center frequency does not meet your requirements, you can modify the equipment or component's value and repeat the simulation until the desired characteristics are achieved. Lastly, you can start to document the result, which will be needed is the record the value of the bandwidth and center frequency obtained from the simulation for our further analysis and reference. On into discussion and simulation at 20 Hz center frequency. The characteristic of a band stop filter are exactly opposite of the band pass filter characteristic. A band stop filter is made to weaken or reject a certain frequency range while allowing other frequencies to pass. We can go over the features and use of a band stop filter with a 20 Hz center frequency. As for filter configuration, we can use passive filters to create a band stop filter that is centered on the frequency of 20 Hz. The passive band filter can be used to isolate or filter out certain frequencies that lie within a particular band or range of frequencies. The stop band of a band stop filter is typically defined by two cutoff frequencies. In this instance, we would choose lower cutoff frequencies that are just under 20 Hz and upper cutoff frequencies that are just over 20 Hz. As you can see based on the example of the band stop graph below, in practice, due to the capacitor switching mechanism in the high pass and low pass filter, the output characteristics are not same as that of in the ideal filter. The pass band gain must be equal to low pass filter and high pass filter. The frequency response of band stop filter is shown below, and ideal lines indicates in the graph is the practical response as the below figure. The bandwidth is taken across the lower and higher cutoff frequencies. According to the ideal filter, the pass band must have the gain as Amax and Amax and a stop band must have a zero gain. In practice, there will be some transition region. We can measure the pass band ripple and stop band ripple as follow. Pass band ripple equal to negative 20 log 10 in bracket 1 minus delta P close bracket decibels, and for stop band ripple equals to negative 20 log 10 open bracket delta S close bracket decibel, where delta P equals to magnitude response of the pass band filter and delta S is equal to magnitude response of the stop band filter. The typical stop bandwidth of the band stop filter is 1 to 2 decades. The highest frequency eliminated is 10 to 100 times the lowest frequency eliminated. The stop band breadth is based on the difference between these frequencies. Various applications can be used, such as in electrocardiogram (ECG) or electroencephalogram (EEG) measurements. A band stop filter at 20 Hz can remove interference caused by power line noise and muscular artifacts. Coming to the end, in conclusion, band stop filters are an essential tool for a wide range of industries, including telecommunications, audio engineering, and medical equipment. By selectively blocking specific frequencies, this filter can help improve the performance and reliability of various systems and devices. We have discussed the benefits of using bandstop filters, how they work, the different types available, and their application in various industries. It is clear that bandstop filters play a crucial role in ensuring optimal performance and preventing interference in many different settings. If you would like to learn more about bandstop filter or have any questions about this presentation, please don't hesitate to ask. We encourage you to explore this topic further and discover the many ways in which bandstop filter can be used to improve the performance and reliability of your own system and devices. Thank you for your times. Thank you for your attention, and please, again, if you guys have any questions, please do let us know and we will try to answer as soon as we can. Thank you and have a great day.